What if the most violent objects in the universe are not endings but beginnings? What if the abyss, the symbol of absolute annihilation, is also a crucible of creation, a cosmic engine of unimaginable power? For decades we pictured them as silent, motionless plug holes in the fabric of space-time cosmic tombstones marking the graves of colossal stars. We saw a perfect sphere of darkness, a one-way door to oblivion from which nothing, not even light, could ever return. This image, born from the first successful wrestling match with Einstein's terrifying equations, has burrowed deep into our collective imagination. It is a simple, elegant, and profoundly misleading picture of the truth. It captures the horror of the black hole, but it completely misses the glory. The universe you see is not a static museum of curiosities. It is a dynamic, swirling, evolving symphony of motion. From the hum of the smallest subatomic particle to the majestic sweep of a galaxy's spiral arms, everything is in motion. Everything spins. And when the largest stars in the cosmos die, they do not simply fade to black. They collapse, yes, but they bring their immense rotational momentum with them, compressing it into a volume so infinitesimally small that the consequences defy all terrestrial intuition. The popular conception of a black hole, this perfect orb of shadow, is what physicists call a Schwarzschild black hole. It is a creature of pure, unadulterated gravity defined by a single property: its mass. It doesn't rotate, it has no electric charge. It is a mathematical ideal, a perfect prisoner trapped in a perfect cage of its own making. For half a century after Einstein revolutionized our understanding of gravity, this was the only black hole we truly knew. Its central feature, the singularity, was a point of infinite density and zero volume, a place where the laws of physics as we understand them simply cease to exist. All paths within its event horizon, the famed point of no return, led directly and inexorably to this single central point of destruction. It is a destination, an end point, a full stop at the end of a cosmic sentence. This vision offered a clean, if terrifying, resolution to the problem of gravitational collapse. It presented a universe with tidy monsters, predictable in their hunger, simple in their anatomy. But nature is rarely so simple, so clean. The universe is messy, chaotic, and gloriously complex. The assumption of a non-spinning black hole was a necessary simplification, a first step into a dark and uncharted territory. But it was always haunted by a fundamental contradiction. The stars that give birth to these behemoths are not static spheres of gas. They are spinning, often ferociously turning on their axes for millions or billions of years. The law of conservation of angular momentum is one of the most fundamental and unbreakable rules of the cosmic game. It's the same principle that causes a figure skater to spin faster when they pull their arms in. As a collapsing star's matter is crushed inward by its own relentless gravity, its rotational speed must increase dramatically. Imagine a star hundreds of times the size of our sun spinning once every few days. Now imagine crushing that entire star down into a space smaller than a city. The resulting object wouldn't just be spinning, it would be a vortex of space-time itself, a gravitational gyroscope whipping the very fabric of reality around with it at nearly the speed of light. To ignore this spin, to pretend it simply vanishes in the final cataclysm, is to ignore the most dynamic and energetic aspect of the object's inheritance. For 50 years, the full complexity of Einstein's general theory of relativity kept the true nature of these spinning behemoths locked away. His field equations, a set of 10 interlocking differential equations, are notoriously difficult to solve. Finding a solution that described the gravitational field outside a simple, non-rotating spherical mass was a monumental achievement by Carl Schwarzschild in 1916. But adding rotation into the mix, accounting for the twisting and dragging of space-time, elevated the problem to an entirely different order of magnitude. It seemed for a time to be mathematically intractable. The greatest minds in physics wrestled with the problem, searching for a key, a hidden symmetry, anything that would unlock the equations for a rotating mass. They failed. The universe, it seemed, was guarding its most extreme secret with a fortress of mathematics. Then, in 1963, came the breakthrough. It didn't arrive with the fanfare of a major discovery announced from a world-renowned institution. It came quietly from the mind of a brilliant but then relatively unknown New Zealand mathematician named Roy Kerr. Working in Texas, Kerr possessed a unique geometric insight that allowed him to see through the formidable complexity. He wasn't just manipulating symbols, he was visualizing the shape of space-time. And in a moment of profound inspiration, he found the exact solution, the one that had eluded science for 5 decades. He wrote it down, a series of elegant, almost deceptively simple-looking equations. What he had written was not merely a correction or an addendum to the old model. It was a revolution. This solution, now known as the Kerr Metric, didn't just add spin to the black hole, it fundamentally transformed it from a passive cosmic sinkhole into an active, terrifying, and unbelievably powerful dynamo. It shattered the simple picture of a spherical tomb and replaced it with a vision of a celestial engine whose inner workings are stranger than any science fiction author ever dared to dream. This documentary is the story of that revolution. We're going on a journey not just into the heart of a black hole, but into the labyrinthine beauty of the mathematics that describes it. We will peel back the layers of the Kerr Metric to reveal a universe far more intricate and dynamic than we ever imagined. To truly appreciate the paradigm shift that Kerr instigated, we must first linger on the world he shattered. The Schwarzschild black hole is an object of profound simplicity. Its event horizon, the boundary that seals it off from the rest of the universe, is a perfect sphere. Cross this boundary and your fate is sealed. Your future contains only one possible destination, the central singularity. Every possible path you could take, every direction you could struggle towards, bends inexorably toward that single point of infinite density. It is the ultimate cosmic prison where all of space flows in one direction downward into the abyss. There is no escape, no reprieve. Time and space become warped in the most extreme way imaginable. For an observer inside the horizon, time itself flows towards the singularity just as space does. The future is not a direction you can choose. It is a physical place you are destined to crash into. This picture, while horrifying, is also deeply symmetrical and in its own way reassuringly predictable. It is a monster, but a monster with simple rules. It waits patiently for matter to fall in. It does not reach out. It does not stir the space around it. It is a passive gravitational predator, a silent dark sphere hanging in the void. For astronomers and physicists, it was a vital theoretical tool, a foundational concept upon which theories of galactic centers and stellar death could be built. But it was built on that one glaring omission, the lack of spin. It was a portrait of a king without his crown, a warrior without his sword. Roy Kerr's solution gave the king his crown, and in doing so revealed him to be something far more than a mere monarch. The Kerr Metric described a black hole that was no longer a perfect sphere. Its immense rotational velocity forces spacetime to bulge at its equator, much like the Earth bulges at its equator due to its own spin. The event horizon of a Kerr black hole is an oblate spheroid, but this is just the beginning of the weirdness, a mere cosmetic change compared to the radical restructuring of reality that occurs both outside and inside this spinning abyss. The first and perhaps most profound new feature revealed by Kerr's mathematics is a region outside the event horizon known as the Ergosphere. The word itself comes from the Greek ergon, meaning work, and for good reason. This is a region where the black hole's power can be put to work. Within the Ergosphere, spacetime itself is being dragged along by the black hole's rotation, a phenomenon known as frame dragging. This is not just a gentle current, it is a spacetime hurricane of incomprehensible ferocity. Inside this region, it is physically impossible to stand still relative to the rest of the universe. The fabric of reality is moving, and you have no choice but to move with it. You're caught in a cosmic whirlpool, and even with the most powerful rockets imaginable firing at full thrust, you cannot stop yourself from being swept along in the direction of the black hole's spin. Think of it this way. Imagine a spinning merry-go-round with a sticky surface. The closer you get to the center, the faster the surface is moving. The Ergosphere is like that, but instead of a wooden platform, it is the very geometry of space and time that is spinning. You can in theory enter the Ergosphere and escape again, provided you don't cross the event horizon that lies within it. But you cannot escape its motion. You are forced to orbit. This is not a suggestion. It is a law of physics woven into the twisted geometry of a Kerr black hole. This bizarre region holds a tantalizing secret, a theoretical mechanism for extracting energy from the black hole itself. The Penrose process conceived by Sir Roger Penrose suggests that a civilization could throw matter into the ergosphere, let it split apart and have one piece fall into the black hole, while the other escapes with more energy than it had originally. The black hole's rotational energy would be converted into the escaping particle's kinetic energy. In essence, the spinning black hole is not just a pit of gravity, it is a colossal flywheel, a storehouse of rotational energy that can in principle be tapped. The silent dead object of the Schwarzschild model is replaced by a celestial power plant. It has been transformed from a tomb into a dynamo capable of powering galactic phenomena, like quasars blasting out jets of energy that can be seen from billions of light years away. Suddenly, black holes were no longer just the end of the line. They were potentially the most powerful engines in the entire universe. The revelations of the Kerr Metric, however, grow even more profound as we venture deeper past the ergosphere and through the event horizon itself. In the old Schwarzschild model, the journey ended at a single point of infinite density. A point. But in Kerr's spinning universe, the singularity is smeared out by rotation. The immense centrifugal forces prevent all the collapsing matter from crushing down into a single, infinitely small point. Instead, the singularity is forced into the shape of a ring, a one-dimensional loop with zero thickness but a finite radius. This ringularity represents a fundamental break with everything we thought we knew about the inner sanctum of a black hole. It is a gravitational edge, a circle of infinite curvature and density, but it is not a point. And this change in shape from a point to a ring opens up a possibility so staggering, so utterly transformative, that it has fueled speculation and scientific debate for over half a century. If you fall into a Schwarzschild black hole, you're doomed to hit the point singularity. There is no alternative. But if you fall into a Kerr black hole, it is theoretically possible to avoid the ring. You could, with perfect navigation, dive through the centre of the ring like a pilot flying through a hoop. And the question that has haunted physics ever since Kerr penned his solution is what lies on the other side. Kerr's mathematics suggests something extraordinary. Passing through the ring, singularity would not be an endpoint. It would be a gateway. The equations describe a bridge, a tunnel through the fabric of space-time leading elsewhere. Perhaps to another point in our own universe, instantly traversing vast distances of space and time. Or perhaps even more fantastically to another universe entirely a separate reality, with its own laws, its own stars, its own history. This is the theoretical basis for the traversable wormhole, a concept long relegated to the realm of fiction, but which emerges naturally from the most accurate mathematical description we have of a real-world object. Now, the physical practicalities of such a journey are immensely daunting, perhaps impossible. The gravitational forces, the intense radiation, the inherent instability of such a structure all present colossal barriers. But the mere fact that the possibility exists within the framework of our best theory of gravity is a testament to the revolution Kerr unleashed. He didn't just find a new type of object, he may have found a new kind of physics, a new topology of reality. He replaced a dead end with a doorway. He transformed the ultimate prison into a potential portal. This is the promise and the puzzle of the spinning black hole. This is the story we will now unravel. We will journey from the swirling accretion disks that feed these monsters, where matter is heated to millions of degrees and shredded by tidal forces, to the storm of dragged space-time in the ergosphere. We will explore the mechanics of energy extraction, witnessing how these objects can power the most luminous events in the cosmos. Then we will take the ultimate plunge, crossing the dual event horizons of the Kerr black hole and confronting the mind-altering geometry that lies within. We will navigate the treacherous path towards the ringularity, exploring the theoretical possibilities of what might lie beyond. This is a story about more than just collapsed stars. It is a story about the fundamental nature of space-time and reality itself. It is a detective story where the clues are written in the language of tensor calculus and the crime scene is the entire cosmos. The Kerr Metric is our key, our map to this hidden territory. It is the mathematical scroll that allows us to read the universe's most violent and powerful secrets. The simple static monster is dead. In its place stands a spinning, vibrant and infinitely more complex titan, a celestial engine that challenges our most basic assumptions about our place in the universe and the limits of what is possible. The journey begins now. What if the most profound truths about our universe were first revealed not as elegant insights but as mathematical monsters? What if a theory designed to describe the graceful dance of planets and the majestic sweep of galaxies accidentally birthed an idea so abhorrent, so contrary to all intuition, that its own creator refused to believe it could be real? This is not a fanciful question. It is the strange and unsettling origin story of the object we have come to call a black hole. Its genesis lies in the single greatest intellectual achievement of the 20th century, Albert Einstein's theory of general relativity. In 1915, he gifted humanity a new cosmic language, a way to understand that we do not live on a static stage where objects are merely pulled by an invisible force. Instead, we're adrift on a dynamic four-dimensional ocean called space-time. Einstein's revolutionary vision was that massive objects do not pull on each other directly. They reshape the very geometry of the universe around them. A star, a planet, even your own body creates a subtle depression in the fabric of space-time, and what we perceive as gravity is simply the sensation of following the resulting curves. It was a symphony of cosmic cause and effect, where matter tells space-time how to curve, and the curvature of space-time tells matter how to move. The equations he produced were a set of 10 intricate interlocking mathematical statements, a divine blueprint for the cosmos. Yet like any powerful new language, it could be used to write sentences its author never intended. The ink was barely dry on his masterpiece when the first truly terrifying prediction began to emerge, not from an astronomical observatory, but from the mud and chaos of the First World War. From the cauldron of the Russian front, a letter arrived in Berlin. It was from a German physicist and astronomer named Karl Schwarzschild, a man who, between calculating artillery trajectories, had somehow found the intellectual clarity to tackle Einstein's labyrinthine equations. He sought to find the very first exact solution to describe the gravitational field outside a single simple, spherical object like a star. It was an act of pure mathematical virtuosity, accomplished under the most brutal conditions imaginable. Einstein was astounded by its elegance. Schwarzschild had navigated the complexities and delivered a pristine, perfect description of how space-time warps around a solitary, non-rotating mass. But buried deep within his beautiful solution was a feature so bizarre it felt like a flaw in the code of reality itself. Schwarzschild's math showed that if you could compress any amount of matter down to a sufficiently small size, its gravity would become overwhelmingly, infinitely powerful. There existed a critical boundary, a specific radius for any given mass, which if crossed would trigger an irreversible collapse. At the centre of this collapse, the equations broke down completely. They screamed of a point of zero volume and infinite density, a place where the curvature of space-time becomes limitless, and all the known laws of physics simply cease to function. He had discovered the singularity. This wasn't just a new kind of star. It was a mathematical phantom, a point of absolute rupture in the cosmic fabric, a terminal disease for which space-time itself had no cure. It was a prediction so extreme, so nonsensical, that it seemed nature must have a way to forbid it. The scientific community, including Einstein himself, recoiled. For years, this Schwarzschild singularity was treated as a pathological artifact of the mathematics, not a physical possibility. It was a ghost in the machine of relativity, a warning sign that the theory was being pushed beyond its limits. Einstein was convinced that some yet unknown physical principle, perhaps the quantum pressures within matter, would always step in to prevent such a catastrophic collapse. Nature, he believed, would not permit the formation of these gravitational monstrosities. The idea was an intellectual poison, suggesting that the universe contained points of utter annihilation, places from which nothing, not even information, could ever return. It was a one-way door to nowhere. For decades, the concept languished in the twilight realm of theoretical curiosities. It was a clever puzzle for physicists to debate, but surely not a blueprint for a real object you could find in the sky. The universe we saw was filled with stable stars, predictable nebulae, and orderly galaxies. It was a cosmos of light and motion, not one haunted by pockets of infinite darkness and finality. The skepticism was so profound that even the term black hole would not be coined for another 50 years. They were simply frozen stars, collapsed objects, or more commonly mathematical aberrations that were best ignored. But the universe is under no obligation to conform to our sense of comfort or reason. The equations were intransigent. They did not care about our disbelief. Slowly, painstakingly, the theoretical ground began to shift. In the late 1930s, J. Robert Oppenheimer and his students began to explore the life cycles of the most massive stars. Their calculations led them to a chilling conclusion. When a star many times more massive than our Sun exhausts its nuclear fuel, there is nothing, absolutely nothing, that can halt its gravitational collapse. The outward push of fusion energy that had supported it for billions of years vanishes in an instant, and the star's own immense weight becomes its executioner. The pressures Einstein had hoped would save reality from the singularity were not strong enough. The star, they proved, would indeed crush itself down past that critical point of no return. The mathematical phantom was threatening to become flesh. With this dawning realization, physicists were forced to look again at Schwarzschild's solution, not as a curiosity but as a prophecy, and they had to confront the true nature of that boundary. He had discovered the shell that separates the monster from the rest of the universe. We call it the event horizon. It is perhaps the most profound and unsettling concept in all of physics, for it is not a surface you can touch or see. It is a boundary in space-time itself. It is a one-way membrane, a causal precipice, a waterfall of reality flowing inwards at the speed of light. Imagine you are in a spaceship approaching this invisible sphere. From a distance, you would see nothing but the distorted light of the stars behind it, their images bent and warped by the immense gravity. As you draw closer, time for you would seem to pass normally. Your instruments would register an ever-increasing gravitational pull, but the journey would feel navigable. The moment you cross the event horizon, however, everything changes, not for you, but for the very nature of your future. In that single, silent, imperceptible instant, you have surrendered your agency to the cosmos. Inside the horizon, the curvature of space-time is so extreme that all possible paths, every single trajectory you could ever take, now lead in only one direction, inwards towards the central singularity. The distinction between space and time flips. The dimension that was once forward in space becomes forward in time. Trying to pull away from the singularity is now as impossible as trying to travel back to yesterday. The future is no longer a branching tree of possibilities, it is a single inescapable point. For an observer watching you from a safe distance, your fate would appear different. They would see your ship slow down, its light becoming redder and dimmer as it fights the ferocious gravity. They would see you approach the horizon but never quite reach it, frozen for an eternity at the edge of the abyss. But for you, the journey continues, a final swift and silent fall into the heart of the enigma where space and time themselves come to an end. This was the classical black hole, the beast born from Schwarzschild's wartime calculations, a perfect spherical static prison of gravity. For nearly half a century, this was the only black hole we knew. It was a terrifying and compelling image, a cosmic scar of perfect symmetry. It had a singularity at its heart and an event horizon as its immutable cage. It had mass and it had a location, but it had nothing else. It was an object of stark simplicity, a gravitational anchor holding a piece of space-time captive. Yet in this very simplicity there was a deep and troubling problem, a flaw so fundamental it should have been obvious from the start. We had conceived of a cosmic object that was perfectly still, an object without spin, and that in our universe is a profound impossibility. Take a look anywhere. The world you're on is spinning, creating the cycle of day and night. The moon that orbits us is spinning, though it keeps one face tidally locked towards us. The Earth and its celestial partner are orbiting the Sun, a vast ball of plasma that completes a rotation every 27 days. Our entire solar system is in motion, hurtling through the Milky Way galaxy, which is itself a colossal spinning pinwheel of 100 billion stars. Galaxies in turn form clusters that rotate around a common centre of gravity. From the smallest asteroid to the largest supercluster, the universe is a place of ceaseless motion, a grand cosmic waltz of angular momentum. Everything spins. It is a fundamental property of matter, a conserved quantity as basic as energy. The stars that give birth to black holes are certainly not static. They rotate, some of them spinning so violently that they flatten into oblate spheroids, their equators bulging outwards from the centrifugal force. So how could it be? How could a star born spinning live its life spinning, and then in its final cataclysmic death collapse into an object that was perfectly unnaturally still? Where did all that angular momentum, all that rotational energy simply go? It was a glaring contradiction, a detail that physicists had to willfully ignore for decades because the alternative was simply too difficult to contemplate. Schwarzschild's solution was a masterpiece of calculation for an idealized, impossible scenario. It described a black hole that could never truly exist in our dynamic swirling cosmos. The real universe demanded a new kind of monster, a black hole that spun. The challenge was immense. Adding rotation to Einstein's equations transforms them from merely difficult to almost impossibly complex. The elegant spherical symmetry that made Schwarzschild's solution possible is shattered. A spinning mass doesn't just curve space-time, it actively drags it, twisting the very fabric of reality into a vortex. The mathematics needed to describe such a gravitational whirlpool were beyond the reach of the world's greatest minds for nearly 50 years. Physics was left in a state of deep uncertainty, armed with a model for a black hole that was fundamentally incomplete, a placeholder for a deeper truth. The search was on for a new solution, for the mathematical key that would unlock the secrets of the spinning abyss. A solution that would not only be more accurate, but would reveal that the universe's most extreme objects were stranger, more powerful, and more wonderfully complex than we had ever dared to imagine. And so the elegant simplicity of Schwarzschild's silent, motionless universe began to feel less like a triumph and more like a beautifully crafted cage. It was a perfect answer to an imperfect question. Because the real cosmos, the one you and I inhabit, is a place of ceaseless motion. Planets pirouette, stars cartwheel, and entire galaxies spin like colossal celestial frisbees. Nothing truly stands still. This universal dance of angular momentum was the ghost in Einstein's machine, the glaring omission that haunted the sleep of every relativist. If a star spins, and it must then, the black hole it leaves behind must inherit that spin, it must carry that cosmic momentum into its abyss. Yet the mathematics that so perfectly described a static point of infinite density utterly shattered when faced with this simple, undeniable reality. The challenge was thrown down a gauntlet laid at the feet of the world's greatest minds: solve Einstein's equations for a spinning black hole. It sounded like the next logical step, a mere iteration on an existing masterpiece. But it would become one of the most punishing intellectual expeditions of the 20th century. To understand the sheer scale of this mountain, you have to journey back inside the architecture of general relativity itself. Einstein's field equations are not a simple set of instructions, like a recipe for the cosmos. They are a conversation, a terrifyingly complex self-referential dialogue between matter and geometry. On one side of the equation, you have the universe's substance, its mass, its energy, its pressure, its momentum. On the other side, you have the shape of space-time itself, the very fabric of reality. The equation states that matter tells space-time how to curve, but here is the devastating feedback loop that newly curved space-time then tells matter how to move. This is what mathematicians call nonlinearity. For a non-spinning black hole, the problem was just barely manageable. The symmetry was perfect, a perfect sphere. You could isolate the variables, hold them still, and the gravitational conversation, while profound, was at least polite. But the moment you add spin, the conversation becomes a shouting match, where every participant talks over everyone else. Imagine trying to describe the ripples in a pond, but with a twist. Every ripple you describe instantly generates its own new set of ripples, and those new ripples alter the very nature of the water they travel through, changing its density and depth. And that change in the water in turn alters the shape of all the ripples that came before. It's a serpent eating its own tail forever. This is what spin did to Einstein's equations. The rotation of the central mass doesn't just warp space-time, it drags space-time along with it. Space-time itself is pulled into a ferocious whirling vortex. This frame-dragging effect, a prediction as bizarre as any in physics, adds an impossible layer of complexity. The energy of the black hole's own spin becomes a source of its own gravity. The rotation feeds back into the curvature, which then alters the rotation's influence on the curvature. The equations began to bloom, branching into a monstrous forest of interconnected terms, a thicket of tensors and derivatives from which no path seemed to lead out. The brightest lights in physics descended upon this problem. Titans of the field, labouring in the hallowed halls of Princeton, Cambridge and Caltech, filled chalkboards with calculations that stretched for days, only to end in contradictions or impenetrable complexity. They tried approximations, chipping away at the edges of the problem, hoping to find a hint of the central truth. They imagined a very slowly spinning black hole, hoping the equations might be simpler if the rotation was just a whisper. But even these perturbative methods yielded a mathematical monstrosity. The solutions were messy, infinitely long and profoundly ugly. And if there is one thing that guides theoretical physicists, it is a deeply held faith that the fundamental laws of the universe must be elegant. They must be beautiful. This was not beautiful. This was a train wreck. For nearly half a century after Schwarzschild laid the first cornerstone, the rotating black hole remained a locked room, a mathematical enigma. The consensus in the rarefied air of theoretical physics began to solidify into a grim certainty. An exact, clean solution probably didn't exist. Perhaps the universe at this extreme edge of reality was simply messy. Perhaps there was no elegant key, no simple phrase that could unlock this gravitational grimoire. The problem was a siren call luring researchers onto the rocks of mathematical insanity. Many of the field's elders began to warn their graduate students away from it, advising them to choose a problem that might actually be solved within a human lifetime. The spinning black hole was becoming a career graveyard. And it is in this atmosphere of exhaustion and accepted impossibility that our story turns. It turns away from the celebrated centres of theoretical physics, away from the famous names who had already wrestled with the beast and been thrown. It turns to a mind that worked differently, a mind forged not in the crucible of physics, but in the more abstract, more rigorous world of pure mathematics. Our story turns to a young man from New Zealand, an outsider in almost every sense of the word. His name was Roy Kerr. Kerr was not your archetypal physicist dreaming of galaxies and nebulae. He was a mathematician, a geometer. He saw the universe not as a collection of particles and forces, but as a landscape of shapes, surfaces and symmetries. His native language was the language of differential geometry, a grammar of pure form. And when he looked at the problem of the spinning black hole, he didn't see a physical object. He saw a mathematical structure that had been wrongly described. He felt with a mathematician's intuition that everyone else was asking the question in the wrong language. By the early 1960s, Kerr had found his way to the University of Texas at Austin, a burgeoning centre for relativity research. But even there, he remained a solitary figure. He was not part of the core teams attacking the big fashionable problems. He preferred to work alone often, late into the night, guided by his own compass. He possessed a quiet, staggering confidence in his own abilities, a necessary armour for someone about to challenge a problem that had humbled a generation of geniuses. He saw the failures of others not as a warning that the mountain was unclimbable, but as evidence that they were all using the wrong path. They were trying to force a solution out of the equations through brute computational strength, hacking through the jungle of nonlinearity. Kerr believed the path wasn't through the jungle but over it. He suspected there had to be a hidden symmetry, a new perspective, a mathematical transformation that would make the entire complex structure collapse into beautiful simplicity, like a child's pop-up book. His search was not for a calculation, but for a viewpoint. This is a fundamentally different approach. A physicist builds a bridge by testing the strength of every beam and rivet. A mathematician like Kerr first tries to prove that a bridge is even possible, and that if it is, it must possess a certain form. He wasn't trying to solve the equations head-on. He was trying to find the unique mathematical space in which the solution was allowed to live. His process was an arduous, almost monastic devotion to abstract thought. Imagine a cartographer tasked with mapping a continent that reshapes itself with every step he takes. This was Kerr's world. He would spend countless hours manipulating symbols, searching for patterns in the algebraic noise. He was looking for a very specific kind of mathematical object, a set of coordinates that could tame the space-time vortex. The standard coordinates, the familiar grid lines of latitude and longitude we project onto our world, were useless. In the swirling chaos around a spinning black hole, these grid lines are twisted into a meaningless tangle. You need a coordinate system that spins and flows along with the distortion, a grid that is itself part of the gravitational river. Kerr's colleagues would see him staring intently at a page of equations for hours, not writing, just looking. He was not calculating, he was navigating. He was trying to develop a feel for the shape of the problem to sense its deep structure beneath the surface of snarled algebra. This is the lonely, unglamorous reality of theoretical breakthroughs. It isn't a frenzy of chalkboard scribbling. It is a long, patient, and often fruitless immersion in a sea of abstraction. It is the willingness to hold dozens of ferociously complex ideas in your mind at once, turning them over and over, searching for a connection that no one has ever seen before. For months, the search yielded nothing. The labyrinth seemed to have no exit. He followed intricate mathematical paths that would, after weeks of painstaking work, lead him right back to where he started. The sheer mental stamina required is difficult to comprehend. It is one thing to face a difficult problem. It is another to face a problem that the world's most brilliant people have already declared impossible. Every dead end, every failed attempt carried the heavy weight of that consensus. Every calculation that dissolved into absurdity was another voice whispering that he was wasting his time. But Kerr's mathematical intuition was relentless. He had a deep abiding faith in the power of symmetry. He knew that nature at its most fundamental level preferred elegance. The ugliness of the previous attempts was to him the ultimate proof that they were wrong. The universe would not build something so important on such messy foundations. He began to focus on a particular set of mathematical tools known as spinors and null tetrades. These were advanced, almost esoteric concepts far from the standard toolkit of most relativists at the time. They allowed him to slice up space-time in a new way, not into cubes of space and ticks of a clock, but into pathways of light. He was reimagining the fabric of reality as a weave of light rays. This was the shift in perspective he'd been searching for. By describing the geometry of space-time in terms of the paths that light would take, he was letting the physics guide his mathematics. The gravitational vortex around a spinning black hole drags light along with it, so by using a coordinate system built from light itself, he was creating a map that was born of the territory it was meant to describe. The equations, when translated into this new light-centric language, began to change. The monstrous tangled terms did not vanish, not at first, but they began to rearrange themselves. Patterns started to emerge from the chaos. 2 terms here would cancel out 2 terms over there. A long complex expression would suddenly be revealed as the square of a much simpler one. It was like watching a scrambled message slowly resolve itself into coherent words. The mathematical serpent was beginning to calm, to uncoil. We can only imagine the rising excitement, the electric thrill that must have coursed through him. After months, perhaps years of solitary struggle in the dark, a flicker of light. He was on the right path. The jungle was starting to thin and he could sense an open clearing just ahead. The process accelerated. Days and nights blurred into a single continuous stream of thought, a final, feverish push. He refined his coordinates, sharpened his mathematical tools, and with every step the baroque complexity of the problem continued to collapse, folding in on itself. The equations were simplifying, becoming cleaner, more compact, more beautiful. And then it happened. Not in a sudden flash of lightning, but as the final logical inevitable step at the end of a long and deliberate path. There on a sheet of paper was a solution. It was an exact solution to the full, terrifying, nonlinear Einstein field equations for a rotating, uncharged mass. It was not an approximation. It was not an infinitely long, messy series. It was compact. It was closed. And it was breathtakingly elegant. It was built upon just 2 parameters, 2 simple numbers that told you everything you needed to know. The mass of the black hole and the speed of its spin. That was it. From those 2 inputs, his solution could describe the entire 4-dimensional, twisted, terrifying and majestic geometry of space-time around any spinning black hole in the universe. He checked his work, then checked it again. There were no mistakes. The brutal half-century-long siege was over. The mathematical Everest had been climbed. Roy Kerr, the quiet mathematician from the other side of the world, had found the key. He held in his hands the blueprint for one of the most extreme and enigmatic objects in all of creation. but finding a solution and understanding what it means are two vastly different things. And as Kerr and his colleagues began to tentatively explore the bizarre new universe described by his equations, they would soon realize that the mystery was only just beginning. The solution he had uncovered was not just a description of a spinning star. It was a gateway to a reality stranger than any of them had ever dared to imagine. For decades, the search remained a ghost story told in the language of mathematics. Physicists chased a phantom and elusive solution that they knew with absolute certainty must exist somewhere within the labyrinth of Einstein's equations. The universe, after all, is a realm of spin. Planets pirouette, stars whirl, galaxies cartwheel in a majestic celestial ballet that has played out for billions of years. Everything with mass from the smallest asteroid to the largest supercluster possesses some measure of angular momentum. Yet the only black hole we could describe, the only one our mathematics permitted, was Carl Schwarzschild's impossible creature, a perfectly still, perfectly spherical anomaly, a point of infinite density without a hint of rotation. It was a magnificent achievement, a landmark of human intellect, but it was also a portrait of an object that could not truly exist in our cosmos. It was a theoretical monarch ruling over an empty kingdom. The problem was a monster of complexity. Einstein's field equations are a set of 10 coupled nonlinear partial differential equations, a mathematical beast so ferocious that Einstein himself only ever worked with approximations. Solving them for a simple non-rotating mass was a Herculean task. Introducing rotation, however, turned the challenge into something else entirely. It was like trying to map the surface of a stormy ocean, while simultaneously trying to map the currents twisting beneath it, where every wave and every current influenced every other in an endless chaotic feedback loop. The neat spherical symmetry that made Schwarzschild's solution possible was shattered. The mathematics became a tangled, impenetrable forest. The world's greatest minds in theoretical physics threw themselves at the problem, and for nearly half a century the forest threw them back defeated. The consensus grew that an exact, elegant solution might simply be impossible, that nature's complexity in this extreme case might be beyond the reach of clean, closed-form mathematics. Perhaps the answer could only ever be found in clumsy brute-force computer approximations. The story of the spinning black hole, it seemed, was destined to remain unfinished. Then in 1963, from an unexpected corner of the world, the answer arrived. It didn't come from the established titans at Princeton, Caltech or Cambridge. It came from a brilliant, tenacious and relatively unknown New Zealand mathematician named Roy Kerr. Working in Austin, Texas, far from the main centres of gravitational research, Kerr approached the problem not as a physicist trying to model a star, but as a geometer obsessed with the pure abstract beauty of space-time itself. He was searching for a particular family of elegant solutions to Einstein's equations, driven by mathematical intuition rather than a specific physical goal. And in that search he stumbled upon something extraordinary. He found a key, a hidden symmetry within the equations that everyone else had missed. With it, the tangled forest of mathematics parted, the chaotic feedback loops resolved, and the ferocious beast of nonlinear complexity was tamed. What emerged was a set of equations so compact, so unexpectedly simple, that at first many refused to believe it. This was the Kerr metric. It wasn't an approximation. It wasn't a partial answer. It was the complete, exact and breathtakingly elegant solution for the space-time geometry generated by any and all rotating uncharged masses in the universe. It was the final authoritative word on the spinning black hole. When he first presented his findings, the reaction was muted, tinged with disbelief. The problem had been a graveyard for reputations for 50 years. How could this young mathematician have solved it? But the solution was flawless. It was perfect. When you plugged in a value of 0 for the angular momentum, the Kerr metric seamlessly transformed back into the familiar Schwarzschild metric. It contained the old universe within it, but it also opened the door to a new one, a universe that was far stranger and more dynamic than anyone had dared to imagine. The static, simple sphere was dead. In its place, something terrible and magnificent was born. The Kerr metric was not just a spinning version of the old black hole, it was a fundamental reimagining of space-time at its most extreme. The first and perhaps most jarring revelation was what happened to the singularity. In the Schwarzschild black hole, all the mass of the collapsed star is crushed into an infinitely dense zero-dimensional point, a terrifying geometric spike. But rotation changes everything. The Kerr solution revealed that the relentless inward pull of gravity is partially counteracted by the stupendous centrifugal forces of its own spin. The singularity is no longer able to collapse to a single point. Instead, the spin flings the singularity outwards, smearing it into a new shape. It becomes a ring, an infinitesimally thin, infinitely dense circle of gravitational terror, a halo of oblivion. This ring singularity was a profound discovery. It suggested that if you could somehow survive the journey and approach it from the right angle, you could, in theory, pass through the centre of the ring without ever hitting the singularity itself. What lay on the other side became a subject of frantic, wild speculation, a gateway to another universe, a path into negative space, a wormhole. While these ideas remain purely theoretical, the existence of the ring itself fundamentally altered the internal architecture of a black hole. The structure of its boundary with the outside universe also became vastly more complex. Schwarzschild's black hole had one simple frontier, the event horizon. Cross it and you are lost forever. Kerr's black hole, however, has two nested event horizons, an outer and an inner, like concentric spheres of doom. Crossing the outer horizon still seals your fate, condemning you to fall inward. But the space between the two horizons is a bizarre, distorted realm where the normal rules of cause and effect can begin to fray. The existence of this inner sanctum, this antechamber to the final abyss, was another clue that we were dealing with a completely new kind of entity. But the true revolution, the feature that would forever change our vision of the cosmos, was happening outside the event horizon. It was here that Kerr's mathematics painted a picture of space-time behaving in a way so violent and so counterintuitive it bordered on the supernatural. The discovery had a name that was almost poetic in its implications: frame dragging. We had a hint of this phenomenon before in a weaker form known as the lens-thirring effect. Einstein's theory predicted that any massive rotating object like the Earth itself should weakly twist the fabric of space-time around it. Imagine a heavy ball bearing spinning in a vat of thick honey. As it spins, it doesn't just turn in the honey, it drags the honey closest to it along for the ride, creating a tiny swirling vortex. The Earth does this to space-time, but the effect is so mind-bogglingly small that it took decades of technological advancement and the Gravity Probe B satellite to measure this infinitesimal twist, a deviation of mere milliarc seconds. But what Kerr's solution described was not a gentle swirl. It was a space-time hurricane of unimaginable ferocity. A black hole containing the mass of millions of suns compressed into a tiny volume and spinning at a significant fraction of the speed of light doesn't just weakly twist space-time. It grabs it, wrenches it, and forces it into a violent co-rotating vortex. This is not a force acting through space like magnetism or gravity as Newton envisioned it. This is the space itself, the very grid lines of reality, the fabric of geometry being seized and spun like a colossal gravitational blender. The Kerr Metric provided the precise map of this storm. It showed that as you get closer to the spinning black hole, the frame-dragging effect grows exponentially more powerful. Far away, its influence is negligible. But as you approach, you begin to feel a strange, inexorable pull, not inward, but sideways. It's a cosmic current, the river of space-time itself, flowing around the black hole. To resist it would require you to fire your rockets not against the pull of gravity, but against the flow of the universe, and then you reach a boundary. A critical frontier defined not by gravity, but by the sheer unyielding power of the black hole's spin. This boundary is not the event horizon. It is something else. It is a surface called the static limit, and the region it encloses is known as the Ergosphere. The name comes from the Greek word ergon, meaning work, and it is here in this swirling cosmic antechamber that the laws of physics begin to take on the character of a fever dream. Outside the static limit, you can, with enough thrust, hold your position. You can resist the space-time current and remain stationary relative to the distant stars. But the moment you drift across that invisible threshold and enter the Ergosphere, all possibility of standing still vanishes, instantly. Inside this region, the frame dragging is so absolute, so overpowering, that space-time is being dragged around the black hole faster than the speed of light. This does not mean things inside are breaking the cosmic speed limit, because it is space itself that is moving. It means that to stay still, an object would have to travel faster than light in the opposite direction, which is a physical impossibility. The consequence is absolute. Nothing, not your most powerful rocket ship, not a beam of light not thought itself, can resist the rotation. You're irrevocably captured by the spin. You're forced to orbit with the black hole whether you like it or not. The very concept of stationary ceases to have any meaning here. The ground beneath your feet, the very geometry of existence, is a raging torrent. You can still move around within this torrent. You can fire your rockets to move closer to the event horizon, or crucially to move away and escape. Because unlike the event horizon, the ergosphere is not a one-way membrane. You can enter and you can leave, but you cannot leave without paying a toll. You will be whipped around by the black hole, flung out in a different direction, carrying with you some of its rotational energy. This was the clue hidden in the name Ergosphere. It's a place where work can be done. Kerr's mathematics revealed that this entire region, a vast donut-shaped volume of space-time surrounding the event horizon, is a colossal reservoir of energy. The black hole's rotational energy isn't locked away behind the event horizon. A significant fraction of it, up to 29% of the black hole's total mass energy, is stored here in the open, in the twisted fabric of space-time itself. It is a cosmic flywheel, a gravitational battery of galactic proportions. The implications were staggering. This was not a dead object. This was not a passive cosmic plug hole. The Kerr black hole was an engine, a dynamic, powerful and potentially accessible source of nearly limitless energy. It fundamentally reshaped the mental image of what a black hole is. The Schwarzschild black hole was a simple predator, a trap waiting patiently in the dark. You fall in and you are gone. The story ends. But the Kerr black hole was something more. It was an active participant in the cosmos, a gravitational gyroscope shaping the environment for light years around it. Its ergosphere bulging at the equator where the spin is fastest, and touching the event horizon at the poles where the spin velocity is zero, was a new playground for theoretical physics. It was a place where particles could be created out of nothing, where energy could be extracted from the void. The silent black sphere of the popular imagination was replaced by a swirling dynamic vortex, a cosmic whirlpool churning the fabric of reality. It was a celestial blowtorch that could power jets of plasma screaming out of the hearts of galaxies at near light speed. It was a gravitational anchor, its frame-dragging effect capable of aligning accretion disks and shaping the very structure of galactic nuclei. Roy Kerr's discovery in 1963 was not merely the solution to a long-standing puzzle. It was a paradigm shift. It was the moment our understanding of gravity's ultimate expression graduated from a static portrait to a dynamic living masterpiece. It elevated the black hole from a mere curiosity to a prime mover, a central engine of cosmic evolution. And in the swirling, energetic depths of the ergosphere, it presented us with a tantalizing, almost frightening possibility. If this colossal storehouse of energy exists, if this immense power is not sealed away behind the veil of the event horizon, then a question of profound importance naturally arises. Could this energy ever be harnessed? Could a sufficiently advanced civilization tap into this spinning abyss and draw power directly from the rotation of a black hole? The answer would come from another brilliant mind, and it would unlock a process more fantastic than any science fiction. And so, we find ourselves standing at the precipice. Not of the black hole itself, not yet, but at the edge of a region so profoundly strange, so utterly alien, that it forced physicists to rewrite the very rules of reality. This is the boundary we glimpsed in the swirling chaos, the ergosphere. It is not a physical surface, but a declaration of war on stillness, an invisible frontier where the universe itself forbids you to rest. To enter it is to be conscripted into the black hole's cosmic dance, a waltz from which there is no reprieve. Imagine yourself in a spacecraft engines firing, attempting to hold your position relative to the distant placid stars. Outside the ergosphere, this is a trivial task. But as you cross that intangible line, a new law takes precedence, a law written by the titanic angular momentum of the central engine. Space-time here is not a passive stage. It is a raging, violent river, and it is flowing faster than the speed of light. Not objects in space, but the very fabric of space itself. Your most powerful thrusters, straining at their absolute limit, become utterly meaningless against this inexorable current. The struggle is not against gravity's pull downwards, but against the universe's rotational command sideways. Every particle, every photon, every iota of your existence is caught in this gravitational hurricane. To remain stationary here is as impossible as trying to stand still in the heart of a tornado by running against its winds. The winds are the world itself, and they are moving too fast. You are swept along a helpless captive in a cosmic whirlpool, forced to orbit in the same direction as the black hole spins. There is no choice. There is no negotiation. There is only the spin. This region, this swirling cosmic ghost, can be immense, extending far beyond the event horizon in a flattened oblate spheroid. For the most rapidly spinning black holes, the ergosphere swells into a colossal arena of captured spacetime. It is a place of pure, untamed kinetic energy, a reservoir of rotational power so vast it defies comprehension. The black hole's spin is not merely a curious property. It is a physical resource, a storehouse of cosmic might. And in 1969, a mind of singular genius, Sir Roger Penrose realised that this cosmic tyranny held within it a secret. He saw that this inescapable vortex wasn't just a trap. It was a treasure chest waiting to be unlocked. He devised a thought experiment so audacious, so brilliant, it felt like a heist plan for the gods themselves. It is a method for stealing energy from a black hole. It begins with a sacrifice. You don't fight the current of the ergosphere, you use it. You send a vessel, a probe, a carefully prepared package into this chaotic dance. As it hurtles through the dragged spacetime gaining velocity, it performs a single critical action. It splits in two. Imagine jettisoning a heavy piece of cargo at the perfect moment. One piece, the sacrifice, is aimed deliberately inwards across the final boundary, the event horizon itself. It is given a trajectory that ensures its capture forever. But this is no ordinary disposal of waste. Through the bizarre alchemy of Kerr's geometry, it is possible to arrange this separation in such a way that the doomed fragment enters the black hole with what can only be described as negative energy. Think of it like this. You're in a boat speeding down a river. You throw a heavy anchor backwards against the current with all your might. The effort of that throw the energy you expend pushes your boat forward even faster than the river was already carrying you. The falling piece is the anchor. By casting it into the abyss with negative energy relative to the whole, the remaining piece, the one that did not fall in, is violently kicked outwards by the laws of conservation. It recoils with a furious burst of speed. When it emerges from the maelstrom of the ergosphere, it is moving faster and possesses more energy than the entire single object that first went in. The new energy did not appear from nothing. It was stolen. It was dredged from the very being of the black hole, siphoned directly from its colossal angular momentum. With every successful Penrose process, the black hole spins down just a tiny infinitesimal amount. The cosmic engine slows its rotational energy converted into the kinetic energy of your escaping probe. Repeat this process millions, billions of times, and you could theoretically extract up to 29% of a spinning black hole's total mass energy. The number sounds modest until you do the calculation. For a single solar mass black hole, this represents more energy than our Sun will produce in its entire 10 billion year lifetime. For a supermassive black hole, the energy available is enough to power a galactic civilization for eons. It is the ultimate power source in the universe, forged in the heart of the ultimate predator, a celestial furnace fueled by the twisting of space-time, offering near limitless power to any civilization bold and advanced enough to perform this cosmic larceny. But what if you don't escape? What if your destiny lies inward past the ergosphere, past the point of no return? For the simple, non-spinning black hole, the journey is brutal and short. The event horizon is a singular absolute gateway. Cross it, and you're on an unalterable one-way conveyor belt to the crushing oblivion of the central singularity. The future has only one direction inwards, and only one destination, annihilation. For the Kerr black hole, however, the story is impossibly unbelievably more complex. Its interior is not a simple chute into nothingness. The very spin that creates the ergosphere outside also fundamentally transforms the structure of space-time inside. As you fall through the outer event horizon of a spinning black hole, you would find yourself in a strange new reality. Gravity is still pulling you relentlessly, but the nature of your fall changes. You're not simply being pulled to a central point anymore. Instead of a single monolithic gateway, the Kerr metric predicts two. After you pass the first horizon, the point of no return, you continue to fall through a region of distorted space and time. But then ahead of you lies another frontier, a second inner event horizon known to physicists as the Cauchy horizon. This is a boundary of a different kind. The outer horizon seals your fate from the outside universe. The inner horizon, according to the mathematics, is the boundary where predictability itself breaks down. It is a place where the determined past ceases to be a reliable guide to the infinite possibilities of the future. A place where the deterministic laws of physics, the comforting chain of cause and effect that governs all we know, might unravel completely into pure chaos. Passing through it would be like stepping off the map of logic into a realm where anything that can happen might happen all at once. An infinite cascade of light and energy from the universe's entire history would theoretically strike you at that one instant, a final blinding farewell from the predictable cosmos. Yet if you could somehow survive this storm of infinities, if you could push through this second shimmering veil, you would enter the black hole's true heartland. And there you would discover the greatest secret of the spin. The singularity, that dreaded point of infinite density and destruction, has been transformed. The centrifugal forces born from the black hole's immense rotation have done something miraculous. They have taken the infinitely small point of the non-spinning black hole and flung it outwards, smearing it across space. The singularity is no longer a point. It has become a ring, a circle of zero thickness and infinite density spinning at a phenomenal rate in the equatorial plane, a halo of infinite gravity, a geometric edge of reality itself. This is not merely a cosmetic change, it is a fundamental alteration to the meaning of destiny. A point singularity is an unavoidable endpoint. No matter your trajectory, all paths inside a Schwarzschild black hole end at that central crushing fist. But a ring has a hole in the middle. For the first time in our exploration of these cosmic monsters, the mathematics presents a loophole, a path of potential survival. If your trajectory is perfectly aligned, if you approach the very centre, not in the plane of the ring but perpendicular to it, like threading a cosmic needle, you could in principle pass directly through the centre of the ring singularity. You would not strike the infinitely dense rim. You would fly through the empty space it encloses. In that moment you would have done the impossible. You would have cheated annihilation. You would have faced the end of the universe and flown right through it. And here the story transcends physics and enters the realm of mythology. What lies on the other side, the equations of general relativity when pushed this far, offer an answer so staggering it seems pulled from science fiction. By passing through the ring, you are not simply in the black hole anymore. You have passed through a gateway. The mathematics suggests you would emerge into a new region of space-time. A white hole, a hypothetical cosmic fountain where matter can only flow outwards, the perfect reversal of a black hole. Or perhaps you would find yourself in a different universe, entirely a parallel reality with its own stars, its own galaxies, its own history. Or in the most dizzying possibility of all, you could emerge back into our own universe, but at a completely different point in space and a different moment in time. The ring's singularity in this idealized vision is not just a singularity, it is a bridge, a wormhole, a junction in the cosmic subway system. The spinning black hole is not merely an endpoint, it is a potential gateway to elsewhere. Now we must temper this incredible vision with a harsh dose of reality. This perfect clean journey is almost certainly a mathematical fantasy. The inner sanctum of a Kerr black hole is likely a place of unimaginable violence. Any tiny perturbation, any single photon falling in after you would be infinitely blue-shifted, gaining limitless energy as it approaches the inner horizon. This wall of infinite energy would almost certainly slam this gateway shut, destroying the fragile bridge, and ensuring that nothing, absolutely nothing, could ever complete the journey. The cosmic loophole is likely sealed shut by the very universe it seeks to traverse. The pristine geometry of Kerr's solution is an ideal, a portrait of a black hole in perfect eternal isolation. The real universe is messy, chaotic, and loud, and yet the possibility remains etched into the fabric of space-time. The mathematics does not lie about what could be. It tells us that rotation doesn't just warp space, it carves it. It sculpts new structures, new frontiers, and new possibilities. It transforms a simple prison into a labyrinth of profound complexity with a potential, however fragile, for an exit. It challenges our most fundamental assumption about these objects that they are merely cosmic dead ends. Instead, they might be the most extreme engines of transformation we have ever conceived. Not just graveyards of matter, but perhaps the birthplaces of new journeys we cannot yet even imagine. This revelation forces us to ask a deeper question. If the inside of a spinning black hole is not what we thought, what does that say about the nature of space and time itself? Are there other even stranger geometries lurking in the dark, waiting for us to find them? What other secrets are spinning out there in the silent, violent hearts of the universe's greatest engines? For more than half a century it haunted the blackboards of theoretical physics. Roy Kerr's spinning demon with its twin horizons and naked singularity was a breathtaking feat of intellectual gymnastics, a solution of perfect, terrifying elegance. But it remained just that, a solution. An answer to an equation living only in the pristine, sterile world of mathematics. Did the universe in all its messy and chaotic glory truly forge these space-time whirlpools, or was this intricate cosmic architecture nothing more than a phantom, a ghost in the grand machine of relativity? The quest for proof would demand more than theory. It would require us to become cosmic detectives to search for celestial fingerprints left at the scenes of unimaginable violence, and to build instruments capable of seeing the unseen and hearing the unspeakable. The universe, it turns out, had been screaming the truth at us all along. We just needed to learn how to listen. Our first clues came not from a singular dramatic discovery, but from the faint, persistent flickering of light in the deepest darkness. They came from systems known as X-ray binaries. Imagine a cosmic drama played out between two partners in a deadly gravitational waltz. One a normal star living out its life, the other a black hole, a compact monster of pure gravity. The black hole's immense pull siphons material from its companions, stripping away its outer layers of gas like a predator. This stolen matter doesn't fall straight in. Conservation of angular momentum dictates a different fate. It is drawn into a swirling incandescent disk of superheated plasma, an accretion disk, orbiting the black hole at tremendous speeds. Here, friction and magnetic turbulence heat the gas to millions of degrees, causing it to blaze with a ferocity that makes it one of the brightest objects in the X-ray sky. This disk is our celestial laboratory. The light it emits is a stream of data encoded with the secrets of the abyss it encircles. By analysing the spectrum of these X-rays, astronomers noticed something strange. They were looking for the characteristic signature of iron atoms which emit X-rays at a very specific, well-known energy. But the signal they received was distorted, smeared out. Instead of a sharp, narrow peak in their data, they saw a broad, lopsided profile like a sharp note of music, stretched and warped into a strange chord. This was the black hole's gravitational fingerprint. The immense gravity of the central object was redshifting the light-stealing energy from the photons as they struggled to climb out of the deep gravitational well. Simultaneously, the incredible orbital speeds of the gas in the disk approaching a significant fraction of the speed of light were causing a dramatic Doppler shift. Light from gas moving towards us was blue-shifted to higher energies, while light from gas receding was red-shifted to lower energies. Combined, these effects perfectly explained the broad shape of the signal, but it was the lopsided nature of that signal that held the key. It pointed to something more. It pointed to a twist in space-time itself. For a non-spinning Schwarzschild black hole, there exists a final speed limit for stable orbits, an edge known as the innermost stable circular orbit, or ISCO. Inside this boundary, no stable orbit is possible. Matter is doomed to plunge directly into the singularity. For a simple black hole, this limit is fixed. But for a Kerr black hole, the vortex of space-time created by its spin changes everything. If the disk orbits in the same direction as the black hole's spin, the frame-dragging effect provides a kind of gravitational tailwind. It helps support the orbiting material, allowing it to creep much, much closer to the event horizon, before finally taking the fatal plunge. This means the iron atoms could survive at higher speeds in a more intensely warped region of space-time. The light they emitted would be subjected to even more extreme relativistic effects, stretching the spectral line further and creating a more pronounced, skewed profile. By carefully modelling this lopsided smear of light, we could do the impossible. We could measure how close the disk came to the event horizon, and from that we could calculate the one thing that determined its location, the spin of the black hole itself. Again and again across the sky in dozens of these violent binary systems, the data told an unambiguous story. These black holes were spinning, and many of them were spinning at near the maximum possible rate, whirling space-time into a furious maelstrom just as Kerr's equations predicted. The ghost was beginning to take shape, but these were stellar mass black holes, the remnants of single collapsed stars. What about the true titans of the cosmos, the supermassive black holes that dwell in the hearts of galaxies' monsters, weighing millions or even billions of times the mass of our Sun? Their existence was betrayed by the most luminous objects in the known universe, quasars. A quasar or quasi-stellar object is not a star at all. It is the blinding light of a galactic core, a celestial blowtorch so powerful it can outshine its entire host galaxy of billions of stars. For decades, the energy source behind this cataclysmic output was a profound mystery. What could possibly power such a beacon across billions of light years? The answer, we realized, was the same process seen in X-ray binaries, but scaled up to an almost unimaginable degree. A supermassive black hole gorging itself on a feast of interstellar gas dust and shredded stars. Yet even this scenario presented a problem. There is a fundamental limit to how efficiently matter can be converted into energy. Einstein's famous equation E = mc2 gives us the absolute maximum. When matter falls toward a non-spinning Schwarzschild black hole, the process of accretion is only about 6% efficient. This means only 6% of the mass of the infalling matter is converted into radiant energy. For many of the most powerful quasars we observed, this simply wasn't enough. They were too bright. Their energy output demanded an efficiency engine that was far more powerful, one that could wring 2, 3, even 5 times more energy from the same amount of fuel. There was only one known mechanism in the universe that could achieve such a feat: the spinning space-time of a Kerr black hole. By allowing the accretion disk to orbit closer to the event horizon, the spin of the black hole lets matter fall deeper into the gravitational well before being consumed. This greater fall releases vastly more gravitational potential energy, which is then converted into heat and light, with staggering efficiency reaching upwards of 40% in extreme cases. The frame-dragging effect doesn't just warp space, it supercharges the entire accretion process, turning the galactic core into the most efficient engine in nature. The blinding light of the quasars visible from the edge of the observable universe was not just the light of dying matter, it was a testament broadcast across cosmic history to the rotational energy of a spinning black hole. It was the ultimate confirmation that these space-time vortices were not just curiosities, but the fundamental engines of galactic evolution shaping the cosmos on the grandest of scales. The evidence was compelling, powerful, but still indirect. We were like detectives observing a crime scene from a great distance, inferring the culprit's nature from the chaos left in their wake. To truly prove the case, to move beyond all shadow of a doubt, we needed more. We needed a witness. We needed a photograph. But how do you photograph something that by its very nature devours light? The task seemed impossible, a technological fantasy, a black hole, even a supermassive one like the giant in the centre of the galaxy. Messier 87, some 55 million light-years away, would appear smaller in our sky than an orange on the surface of the moon. To resolve an image that small would require a telescope of unprecedented power. It would require a telescope the size of the Earth itself. So, we built one. The Event Horizon Telescope, or EHT, is not a single instrument, but a global network of radio observatories spread across continents, from the mountains of Chile to the volcanoes of Hawaii, from the Spanish Sierra Nevada to the frozen expanse of the South Pole. Using a technique called very long baseline interferometry, these disparate dishes are synchronized by atomic clocks of astonishing precision, their observations combined by supercomputers to function as a single planetary-scale virtual lens. In April of 2017, this global eye opened and stared into the heart of M87. For days it gathered petabytes of data, not an image, but a torrent of faint radio waves, a cacophony of cosmic static. It would take 2 years of painstaking work of developing new algorithms and cross-checking results between independent teams to turn that static into a picture. And when they finally succeeded, the world held its breath. There it was. Not a simulation, not an artist's impression, a direct image of a black hole's shadow, a perfect circle of darkness, a void in the fabric of reality silhouetted against the glowing chaotic swirl of superheated plasma. It was a monumental achievement, a triumph of human ingenuity that brought a gasp to the world. But for the physicists who had spent their lives studying Kerr's solution, the most profound revelation was not in the darkness, but in the light surrounding it. The ring of light was not uniform, it was lopsided. One side of the accretion disk was conspicuously brilliantly brighter than the other. This wasn't an imperfection in the image. This was it. This was the direct visual confirmation of frame dragging. The black hole at the heart of M87 was spinning, and its spin was oriented in such a way that the gas on one side of the disk was moving toward us, while the gas on the other was moving away. The material hurtling toward our planet-sized telescope had its light amplified and blue shifted by relativistic beaming, making it appear intensely bright. The material receding on the other side was dimmed and redshifted into obscurity. The image was more than just a picture of a hole in space. It was a map of warped space-time. The size of the shadow confirmed the mass predicted by general relativity. The asymmetry of the light was the unmistakable signature of its spin. Roy Kerr's mathematical ghost, once confined to paper and chalk, was now staring back at us from across 500 quintillion kilometers of space. We had finally seen the vortex, and then we heard it. On September 14th, 2015, 2 colossal detectors, one in Louisiana, one in Washington state, felt a shudder ripple through them. The Laser Interferometer, Gravitational Wave Observatory or LIGO, had registered a vibration thousands of times smaller than the nucleus of an atom. It was a wave not of light or of matter, but of space-time itself. The signal, a faint chirp lasting less than a quarter of a second, was the echo of a cataclysm that had occurred 1.3 billion years ago. 2 black holes, one 29 times the mass of the Sun, the other 36, had spiraled into one another in a final violent embrace. As they merged, they unleashed a storm of gravitational waves, a burst of energy more powerful than all the light from all the stars in the observable universe combined. This was the first direct detection of gravitational waves, a discovery that would win the Nobel Prize and open a completely new window onto the cosmos. But buried in that brief ephemeral signal was the ultimate confirmation of Kerr's theory. The event can be broken into 3 parts. The inspiral as the 2 black holes circled each other ever faster, emitting a rising chirp of gravitational waves. The merger, the violent chaotic moment when they became one. And finally the part that mattered most for our story, the ring down. For a fleeting moment, the newly formed black hole was a misshapen wobbling object, a disturbed blob of pure dynamic space-time. It immediately sought to shed these imperfections to settle into its final stable state. As it did, it vibrated, ringing like a struck bell. But this bell was not made of metal, and its ringing was not sound. It was the quivering of space-time itself, broadcasting a final fading symphony of gravitational waves. And here is the crucial point. The precise notes of that symphony, the exact frequencies and decay rates of the ring down, are dictated entirely by just 2 properties of the final black hole: its mass and its spin. A non-spinning Schwarzschild black hole would ring with a single, simple, fundamental tone. But a spinning Kerr black hole is different. Its contorted geometry means it must ring with a specific set of overtones, a unique chord that is its definitive acoustic signature. The equations that predict this signature are derived directly from Kerr's metric. They are among the most complex and beautiful predictions in all of physics. When the LIGO team analysed the ring down from that first historic merger, they found something that sent shivers down their spines. The signal from the heavens was a perfect match. The frequencies, the amplitudes, the decay times, every single detail of the fading gravitational wave signal corresponded precisely to the ringing of a newly formed Kerr black hole with a specific mass and a specific rapid spin. It was the purest test imaginable. There were no confounding variables, no messy accretion disks or interstellar dust. There was only the pure geometry of space-time vibrating in the aftermath of creation. We had not just seen the effects of a spinning black hole, we had heard its voice. We had listened to the fundamental tone of a new Kerr entity being born into the universe. From the smeared light of distant X-rays to the impossible brightness of quasars to a direct photograph of its shadow and the sound of its birth cry, the evidence was overwhelming, incontrovertible. The ghost in the machine was real. Roy Kerr had, through the sheer power of reason and mathematics, uncovered a fundamental truth about the fabric of our reality, decades before we had the tools to prove him right. The spinning black hole was no longer a theoretical curiosity. It was now a confirmed, observable, and utterly essential component of our universe. But confirming its existence was only the beginning. For within the bizarre and paradoxical space-time of the Kerr Metric lie possibilities that challenge our very notions of energy causality and the ultimate fate of matter. The vortex had been found, and now we had to face the terrifying question of what truly lies inside. And so we arrive at the end of our journey, not at a destination, but at a precipice overlooking a new and far more bewildering cosmos. We have walked the razor's edge of an event horizon, navigated the swirling vortex of an ergosphere, and stared into the chilling theoretical abyss of a ring singularity. We have seen a universe once imagined as a silent static stage for gravity's slow waltz, utterly transformed into a dynamic, violent and creative arena, all because of a set of equations born from the mind of one quiet genius. Our voyage began in the deceptive simplicity of a single point, a motionless monster lurking in the dark. Einstein's theory had given us the Schwarzschild black hole, a perfect sphere of inescapable gravity, a cosmic dead end. It was an object of pure termination, a place where space and time ceased to have meaning, a gravitational period at the end of a stellar sentence. For decades, this was the accepted image, a static and somewhat predictable beast that devoured light and information with placid finality. It was a pillar of the universe, yes, but an inert one. It did not act, it merely was. The universe it inhabited felt grand, yet strangely passive. Stars died, matter fell, and these silent traps waited. But this elegant simplicity we now know was a ghost. It was an idealization that could never truly exist in a cosmos defined by motion, a cosmos where everything from the smallest moon to the most colossal galaxy is locked in an endless dance of rotation. The real universe demanded a different kind of monster. It required a demon with dynamism, an engine of incomprehensible power. It needed Roy Kerr's solution. When those intricate equations finally resolved themselves on paper in 1963, they did more than just add spin to a black hole. They injected life chaos and staggering potential into the darkest corners of existence. The Kerr Metric shattered the image of the passive gravitational sink and replaced it with the celestial dynamo. Suddenly the black hole was no longer just a destination for matter, but an active participant in the cosmic drama, a gravitational gyroscope shaping the very fabric of its surroundings. It became a cosmic agent of change, a source of unthinkable energy, a celestial blowtorch capable of launching jets of plasma across thousands of light years, powering quasars that outshine entire galaxies. This spinning behemoth with its frame-dragging vortex forces space-time itself to participate in its rotation, enslaving everything in its vicinity to its will. The universe was no longer a quiet graveyard punctuated by gravitational tombstones. It was a workshop filled with furious spinning engines, each one a testament to the conservation of angular momentum, each one a Kerr black hole. This was the first profound legacy of Kerr's work, the revelation that the most extreme objects in the cosmos are not endpoints, but keystones of cosmic evolution actively sculpting the galaxies they inhabit. This transition from a static point to a dynamic ring, from a simple trap to a complex engine, was not merely a theoretical upgrade. It provided the essential key to unlocking the raw observational data that would begin to pour in from the heavens decades later. When our first gravitational wave detectors, the incredible instruments of LIGO and Virgo, finally felt the whisper of two merging black holes from 1 billion light-years away, what did they hear? They did not hear the simple chime of two Schwarzschild points colliding. They heard a complex song, a chirp rising in frequency and amplitude, a melody rich with the information of two massive spinning bodies caught in a death spiral. To decipher that song, to understand the masses, the distances, and most critically the spins of those colliding objects, astrophysicists needed a precise template. They needed a perfect mathematical description of how spinning masses warp space-time as they whirl around each other at nearly the speed of the light. That template was and is the Kerr Metric. Without it, the gravitational wave signal would be just noise, an incomprehensible cosmic scream. With it, we can reconstruct the event with breathtaking precision. We can witness the final moments of these cosmic titans, we can see how their spins influence their dance, and we can watch the ring down of the newly formed larger black hole as it settles into its final state, a new Kerr black hole, its unique gravitational note radiating across the universe. The Kerr solution is the bedrock of gravitational wave astronomy, the Rosetta Stone that allows us to translate the language of space-time ripples into the physics of the universe's most violent events. It has transformed black holes from theoretical curiosities into observable, measurable, and stunningly real phenomena. Yet the legacy of Kerr's spinning universe extends far beyond what we can currently observe, pushing us into the deepest and most unsettling questions in all of physics. It takes us to the stormy frontier where gravity's smooth, elegant curves crash against the chaotic, uncertain shores of the quantum world. The static Schwarzschild black hole presented a paradox profound enough to shake the foundations of science, the information paradox. If information falls in, can it truly be destroyed forever, violating a fundamental tenet of quantum mechanics? The introduction of spin complicates this puzzle almost beyond imagination. A spinning black hole has more properties than just mass. It has angular momentum. It has a complex internal structure with an inner horizon, a region of bizarre and unstable physics. How does this intricate machinery interact with the quantum foam of spacetime? Does Hawking radiation, the faint quantum glow from a black hole's edge, carry information about its spin? Does the swirling ergosphere, where energy can be extracted, somehow play a role in preserving quantum information, preventing it from being lost to the singularity? These are no longer just philosophical musings. They are active, urgent questions at the heart of the search for a theory of quantum gravity. The holy grail of modern physics that would unite Einstein's world with the quantum realm. The Kerr Metric provides the essential classical background, the precise space-time arena upon which any future quantum theory of gravity must perform. It defines the extreme gravitational conditions that a new theory must be able to explain. It is the immovable object against which we hurl our most advanced ideas, a silent arbiter of what might be possible. The spinning black hole in its glorious complexity has become the ultimate laboratory for testing the limits of our understanding, a place where the two pillars of 20th century physics meet, and where we know with absolute certainty that one or both must break. And it is here, in the purely mathematical realm, where our equations dare to go where our telescopes cannot, that the Kerr Metric offers its most tantalizing and reality-bending vision. For deep within the mathematical heart of the solution lies a feature that has fueled speculation and science fiction for over half a century. Unlike the Schwarzschild black hole, which hides a point-like singularity of infinite density, the Kerr solution predicts a singularity in the shape of a ring, a one-dimensional loop of infinite curvature. This is no mere geometric curiosity. According to the mathematics, this ring singularity is a gateway. The equations suggest that it might be possible theoretically to travel through the centre of that ring, to bypass the infinite gravitational tide and emerge somewhere else in our universe, or perhaps somewhere else entirely. This is the mathematical seed of the traversable wormhole. The Kerr Metric in its purest form describes a bridge connecting our cosmos to another, a feature known as the Einstein-Rosen bridge. Now we must be clear. This is almost certainly a mathematical fiction, an artifact of an idealized solution that ignores the violent instability that would likely slam this cosmic doorway shut the instant it formed. The principle of cosmic censorship, a conjecture that nature abhors such naked singularities, likely protects us from these causal paradoxes. But the very fact that such a structure is a valid logical consequence of Einstein's equations when spin is introduced is a staggering revelation. It tells us that the universe at its most fundamental level might possess a topology, a connectedness that is wildly more complex than our everyday experience suggests. It whispers of possibilities that stretch the very definition of reality. The Kerr Metric serves as a constant, humbling reminder that the universe described by our best theories is profoundly stranger than we can imagine. It forces us to confront the possibility that space-time itself might contain hidden passages, secret corridors woven into its very fabric, all born from the simple ubiquitous act of rotation. So where does this leave us? We stand in the light of a new cosmic dawn, one illuminated by the dark glow of spinning black holes. We have travelled from a conception of the universe as a predictable clockwork machine to one that is active, evolving, and endlessly surprising. We have learned that the darkest objects in the cosmos are also among its most creative, that the points of no return are also the engines of galactic creation. This epic shift in perspective was not delivered by a grand telescope or a particle accelerator. It was delivered by the quiet, persistent effort of the human mind, armed with nothing more than pencil paper and the relentless logic of mathematics. Roy Kerr's solution is one of the supreme achievements of the human intellect, a testament to the almost mystical power of abstract thought to uncover the physical truths of the universe. It is a symphony written in the language of tensor calculus, a perfect and beautiful description of a gravitational titan that we are only now 60 years later beginning to truly see. The elegance of those equations, their ability to predict the precise shape of space-time around a spinning mass, is a profound statement about the deep connection between the mathematical world and the physical one. It tells us that the universe is not just chaotic and random, it is structured, it is logical, and in its own way it is understandable. As you look up into the night sky, into that vast and silent ocean of stars, know that it is not silent at all. It is humming with the energy of rotation. It is churning with the power of billions of gravitational engines, each one a Kerr black hole twisting space-time powering jets and singing a gravitational song that we have only just learned to hear. We do not know what secrets still lie hidden within their swirling depths. We do not know if they guard gateways to other universes or hold the key to a final theory of everything, but we do know that they are there. And we know that our quest to understand them, a quest that began with Einstein and was revolutionized by Kerr, is far from over. The journey into the spinning heart of darkness has only just begun. The universe in all its spinning dynamic glory awaits.